today's quiz, we're going to be investigating the decay of uranium to lead, which is a multi-step process, and it consists of 8 alpha decays and 6 beta decays. And the first question is asking for the first in the series, which is an alpha decay. And so here we're starting with just the plain uranium, right? It's going to decay many times, but the first of these decays is alpha. And when we seek to find the product of this reaction, it's good to lay down what we know. And in this case, it's that we have uranium-238. It's undergoing alpha decay and will make an unknown isotope plus our alpha particle. And that alpha particle is a helium nucleus. This notation shows that it has 2 protons and 4 total mass, the bottom number being the charge, in this case the number of protons, and the top being the total number of mass containing particles, the nucleons, meaning protons and neutrons. And when we balance these equations, the top number on each side has to be the same, the total of the top number, and the bottom number, the total of the bottom number on each side has to be the same. And based on this, we can determine the numbers for the final isotope and its identity. And in this case, it's going to be this one. 90 on the bottom, as 90 plus 2 is 92, to equal the 92 on the left. 134 on the top, as 134 plus 4 equals 238. 234 plus 4 equals 238. Okay, now we know the product of the first step, and we want to know the product of the second step, which is a beta decay. And here we have the exact same process, but note that instead of the alpha particle as one of the products, we have our beta particle. And we can write it as an electron or as the Greek lowercase beta. And in the same way, we want to make sure that the sum of the top numbers is equal and that the sum of the bottom numbers is equal from the left side to the right side. And here that gives us the following. Note that for the bottom number, it's 91 plus -1 on the right. That will make it equal to 90 on the left. And the top, the electron is massless, and so still we have a mass number of 234. These are nuclear decay equations. These are some of the named decay processes that are important to know, and they aren't restricted just to alpha decay, beta decay, etc. The principle behind these nuclear decays is that the sum of the charge and the sum of the mass containing particles is always needing to be the same on both sides. Okay, so now we want to do some more analysis, and we are having this sample of uranium ore. It contains a certain number of moles of uranium and a certain number of moles of lead. And we want to first know how much uranium was initially present, assuming that all the lead came from uranium and that the uranium was not formed into anything else. And so let's write down what we know here, right? Currently we have a certain number of moles of uranium and a certain number of moles of lead. Now, this uranium remains from the initial amount, right? It's a sample of uranium ore, it's been decaying over time, and we know that the uranium that was initially present, some of it is still here, and that's what we have on the top. For the bottom, this is what's decayed, right? Moles of uranium have been decaying into lead over time, and 0.0125 moles are that amount of lead that we have here. And so based on that, what we know initially is that all of the uranium we have currently was still part of this sample, and the lead that's here was that equivalent number of moles of uranium. As the uranium was becoming lead, this 0.0125 moles of lead at the very beginning was uranium. Based on that, we know that initially there were 0.0350 moles of uranium-238. Finally, we want to look at some quantitative evaluation. We have now the half-life of this decay process, and we want to calculate the age of this uranium ore, which is basically to say how long has it been since it was initially all uranium. And since it says uranium ore, we should assume that it is uranium that's forming lead only through this decay process. And this is a first-order decay following first-order kinetics, and basically what we're looking at is an initial amount of 0.0350 moles to a final amount of 0.0225 moles of this uranium. And this is first-order kinetics. We have our first-order integrated rate law, which tells us that the natural log of the uranium we have now is equal to negative kT plus the natural log of the uranium we had initially. And for this, we first need to get the rate constant, which is related to the half-life through the following, which is actually derived right from first-order decay. But basically, the rate constant and the half-life are the same information. How long is it taking for this decay to occur? And so they are able to be calculated based only on the other one. And we get our K value here, 1.54 times 10 to the negative 10 years. We plug everything in basically to our first order decay. This is the only unknown left is our time. And when we solve, we get that the time that has passed is 2.87 times 10 to the 9 years. And this makes sense because we haven't quite gotten to 50% of the uranium remaining, and therefore we haven't quite had one full half-life elapse. We've only had about 2/3 of a half-life pass. Okay, this is one way to solve the problem, but remember we can also solve these first order decays through the following, where we say the fraction of the sample remaining is 1/2 raised to the n power. And for the fraction, we simply take the amount we have at the end divided by the amount we have initially. And this shows that we have 64.3%, or 0.643 is the fraction that we have remaining of the original uranium sample. This is equal to 1/2 to the n. And this is really good for the conceptual idea, n is the number of half-lives, as if one half-life passes, we have half. If two half-lives pass, n equals 2, 1/2 to the n is 1/4, and we'd only have a quarter left. So this version really does kind of have that image of it dividing in half each time, baked in a bit more so than first order decay. Once we have this, we can rearrange. I've multiplied both sides by 2 to the n, and then divided by 0.643, cross multiply if you like, and then we can solve this by taking the base 2 logarithm, and we see that n is equal to 0.637, which means that 0.637 of one half-life has passed. It's not a whole half-life, it's not half a half-life, it is 0.637 of a half-life, so between half and one. With this, we can determine the actual amount of years by taking this fraction and multiplying it by the duration of the half-life, right? If this was half of a half-life, we would take 0.5, multiply it by the half-life. If it was a whole half-life that passed, we would just multiply it by, we just have the half-life. But here, we want 63.7% of a half-life, 0.637, and with that, we actually get the exact same answer as we did before. So it's not necessary to do both of these methods, but I thought that I would show them. Some problems are easier to set up with one versus the other, but all problems can be done with either method, whichever one you prefer.